Good morning, students. Chapter 5, Magnetism and Matter. Yes, we are discussing from the first, what is magnetism, what is magnetism, what is magnetic material. So yes, in this lecture we will understand what is magnetic material. Okay, if you know, if you have one piece of iron, then yes, it does not behave as magnet. But if you do some processes on that iron piece, on that iron bar, after some processes, it behaves as magnet. It behaves as magnet. So yes, there may be a question why it behaves as magnet. Okay, initially it is not magnet, but after some process it behaves as magnet. Then why? What happens? What happens? Okay, so yes, we will discuss about this in this lecture. Magnetic properties of material, and according to some parameters, that is relative permeability, then chi m, that is magnetic susceptibility. There are three types of magnetic material: diamagnetic, paramagnetic and ferromagnetic. Okay, but before that we will see how any magnetic material is magnetized or it has some magnetic moment. We know that each and every object is made up of particles. Particles are made up of molecules. Molecule is made up of atom. Atom is made up of electron, proton and neutron, nucleus. And around that electrons are revolving. Yes, electron is performing two types of motion. Electron. Okay. Orbital motion and spin motion. And yes, remember in chapter number 4 we have proved one theory, that is magnetic moment due to orbital motion of electron. Orbital magnetic moment of electron. See what is concept. See this time. Whenever charge is in motion, when charge is in motion, it forms current, and due to current, magnetic field is produced. Yes or no? Due to current, magnetic field is produced, and we know that current carrying loop behaves as magnetic dipole. So here, each and every electron performs orbital motion and spin motion. So due to this orbital motion, it has orbital magnetic moment. Okay, and due to spin motion, it has spin magnetic moment. Clear about this? Okay, so yes, orbital magnetic moment plus spin magnetic moment, and yes, moment is vector quantity. So yes, this plus is vector addition. It is vector addition. Okay, so vector addition of vector addition of orbital magnetic moment and spin magnetic moment gives resultant magnetic moment of electron. Clear about this? What is first topic? Yes, fundamental particles. Fundamental particles are electron, proton and neutron. They are stationary in nucleus. Electrons are revolving in orbit. They are also performing spin motion. So yes, due to their orbital motion and due to their spin motion, they have orbital magnetic moment and spin magnetic moment. So orbital magnetic moment plus spin magnetic moment means vector addition. It gives magnetic moment of electron. Now, magnetic moment of electrons, summation of vector addition of means sigma of magnetic moment of electron. Magnetic moment of electrons. vector addition of magnetic moment of electrons. It gives magnetic moment of magnetic moment of atom. Magnetic moment of atom. Clear about this? Clear about this? Okay, so yes, it is easy. Yes, it is easy. Vector addition of magnetic moment of electron gives magnetic moment of atom. Now I said each and every object made up of particles are made up of molecules are made up of atoms. Okay, so there are numbers of atoms. There are numbers of atoms. So again, vector addition. Again, vector addition of magnetic moment of atoms. It gives magnetic moment. It gives magnetic moment of material. It gives magnetic moment of material. And at last, if this magnetic moment of material is not equal to zero, then this object is called magnetic material. It is said to be magnetized. Clear about this? Again, at micro level, electron performs orbital and spin motion. Due to that, it has orbital magnetic moment, spin magnetic moment. Vector addition of orbital magnetic moment and spin magnetic moment gives magnetic moment of one electron. Vector addition of magnetic moment of each electron, it gives magnetic moment of atom. Vector addition of magnetic moment of atoms gives magnetic moment of material. And if it is not equal to zero, means material have some resultant magnetic moment, it is said to be magnetized. It behaves as magnet. Clear about this? Yes, at any stage, if motion of electron is such that orbital magnetic moment and spin magnetic moment, their addition becomes zero. Magnetic moment of electron is zero. Then obviously, what is vector addition of magnetic moment of electron? That is magnetic moment of atom, zero. Then total magnetic moment will be zero. Then that object is not said to be magnetized. Clear about this? Yes. So yes, how we can say that some material behaves as magnet like this. Clear about this? Now on basis of such motions and that, the magnetic materials are classified in three groups: diamagnetic material, paramagnetic and ferromagnetic. What is difference between them on basis of chi m, that is magnetic susceptibility, mu r, that is relative permeability, and epsilon. Epsilon is not permittivity. It is a small positive number. So yes, you have to remember this table. Okay, for diamagnetic material, chi m, that is magnetic susceptibility, it is from -1 to 0. For paramagnetic, it is from 0 to epsilon. And for ferromagnetic material, it is very greater than 1. Same relations for mu r, that is relative permeability. And here it is for, with respect to relative permeability of free space, or we can say air. Mu less than 0, mu greater than 0, and here mu is very greater than mu 0. So here from these two we can say, okay, for diamagnetic material, chi m, that is magnetic susceptibility, is negative, less than 0 and between -1. So it is obviously negative. Okay, for paramagnetic material, it is positive. So what is difference? Okay, for diamagnetic material, chi m is negative, and for paramagnetic, chi m is positive. And for ferromagnetic, chi m is very greater than 1. So now, what is difference between diamagnetic material, paramagnetic material and ferromagnetic material? This difference we will discuss in detail. Starting from diamagnetic material. See, diamagnetic materials. Okay, some materials. See, here it is. Electron, orbital magnetic moment, spin, magnetic moment. So how to find magnetic moment of electron, magnetic moment of orbital, and it is spin. If its addition is 0, means magnetic moment of one electron is 0. Yes or no? Then of another electron, obviously 0. Then of another material, obviously 0. Yes or no? Yes or no? Yes. So from the first that level, total magnetic moment becomes 0. Yes or no? Yes. Such material in which orbital motion of electrons and their spins are such that magnetic moment becomes 0. They are called diamagnetic materials. Some examples are, see, the atoms, molecules of gold, copper, silicon, water, etc. do not possess permanent magnetic dipole. What is meaning of this? Do not possess permanent magnetic dipole. We will see its difference, okay? But before that, remember one case. Chapter number 2, electrostatic potential and capacitors. Topic number polar and non-polar dielectrics. Polar and non-polar dielectrics. And remember, non-polar dielectrics. Non-polar means in absence of electric field. In absence of electric field, electric dipole moment is 0. But in presence of electric field, it behaves as dipole, meaning it has some dipole moment. So similar differences here. See, diamagnetic materials, the atoms, molecules of gold, copper, silicon, water, etc. do not possess permanent magnetic dipole. Why? What is reason? What is reason? See, we will understand. Here it is. Here it is. In absence of external electric field, in absence of external magnetic field, the orbital motion of electrons and their spins are such that the total magnetic dipole moment is 0. Yes, you know what is charge, okay? First of all, magnetic moment of electron, then magnetic moment of atom, then magnetic moment of material. If magnetic moment of electron is 0, then obviously magnetic moment of material is also 0. So yes, the orbital motion of electrons and their spins are such that their total magnetic dipole moment is 0. Such materials are called diamagnetic materials. Such magnetic materials are called diamagnetic materials when they are in absence of external electric field. Now when they are placed in external field. So when the diamagnetic material is placed in an external magnetic field, a net magnetic moment in a direction opposite to that of external field is induced in each atom. Yes, you have to remember this point. When the diamagnetic material is placed in an external magnetic field, a net magnetic moment in a direction opposite to that of external field is induced in each atom. How? We will see. See here. Now see what happens when a bar of diamagnetic material is placed in uniform external field. See, it is uniform external field P. It is uniform external field. It is uniform external field B, like this. Okay, uniform external field. In which a bar of diamagnetic material is placed. In which a bar of diamagnetic material is placed. Okay, to see when diamagnetic material is placed in uniform magnetic field, we know that this diamagnetic material is made up of particles made up of molecules, atoms. Yes or no? So yes, in absence of magnetic field, net dipole moment of electron is 0. So net dipole moment of atom is also 0. So net dipole moment becomes 0. But when they are placed in external magnetic field, due to this field, in each and every atom, magnetic dipole is induced such that its magnetic moment is in opposite direction. Its magnetic moment is in opposite direction. Clear about this? Means this diamagnetic material is magnetized. this diamagnetic material is magnetized, but in opposite direction. Clear about this? So yes, due to this diamagnetic material, whatever field is produced, it is in opposite direction. Of external field. Clear about this? Yes or no? So yes, I can say at this pole it behaves as north pole, and this pole of diamagnetic material it behaves as south pole. Clear about this? Now see, in this region, external magnetic field is in this direction. This diamagnetic material is magnetized in opposite direction. So magnetic field lines are in opposite direction. So obviously, when a bar of diamagnetic material is placed in uniform external field, in this region, these two magnetic fields are in opposite direction. So in this region, magnetic field reduces. Clear about this? In this region, magnetic field reduces. Okay, so yes, I can draw another figure. Okay. If it is a diamagnetic material, it becomes north pole, it becomes south pole. So yes, in this region, magnetic field decreases. Clear about this? Yes, in this region, magnetic field decreases. Or we can say magnetic field lines are repelled. Yes or no? Yes. So here, magnetic field lines. Magnetic field lines are repelled. Clear about this topic? And yes, in this region, magnetic field reduces. Clear about this? So yes, in this region, magnetic field is reduced because these two magnetic fields are now in opposite direction. And as these two magnetic fields are in opposite direction, diamagnetic material is magnetized in opposite direction. Chi m is negative. That is, magnetic susceptibility is negative for diamagnetic material. Chi m is negative for diamagnetic material. Clear about this? Okay, so yes, you have to remember this point. First point is when diamagnetic material is placed in uniform external field B. Yes, it is magnetized in opposite direction, and in this region, that is in this bar magnet, magnetic field reduced. Chi m is negative. Okay. Now what happens when a bar of diamagnetic material is placed in non-uniform magnetic field? What happens when it is placed in non-uniform magnetic field? So we will see what happens when it is placed in non-uniform magnetic field. See, here it is. If I have non-uniform magnetic field like this, okay, yes, like this, and here a bar of diamagnetic material is placed. We know that in diamagnetic material it is magnetized in opposite direction, so it will become north pole and it will become south pole. Clear about this? So magnetic field produced will be in opposite direction. Simple. Yes or no? Yes, it is. So yes, here it is magnetized in opposite direction. Now, from figure can easily see, here it is. In this region, magnetic field B is strong. In this region, magnetic field B is weak. So we can say north pole is in strong magnetic field, south pole is in weak magnetic field. Yes or no? Yes or no? Yes. So force acting on this north pole, it is in this direction. that is Fn. That is Fn. Yes or no? And force acting on south pole, that is Fs. That is Fs. Okay. Force acting on north pole. Force acting on north pole. Fn, it is in this direction. And force acting on south pole, it is in this direction. Like positive charge, force acting on positive charge is in direction of magnetic field, and force acting on negative charge, it is in opposite direction. Similarly, clear about this? Clear about this? Okay. So yes, here we have one non-uniform magnetic field. In this non-uniform magnetic field, force acting on north pole and south pole. Force acting on north pole and south pole. It will be in which direction? It will be in which direction? See, it is direction of magnetic field due to magnet. Now we know that magnetic field is from north to south. Yes or no? It is from north to south. This diamagnetic material is magnetized like this. This diamagnetic material is magnetized like this. Is magnetized like this. Then what happens? See, here it is. See, here it is. Okay. Here on this north pole, due to this force acting, it is in this direction. In direction of magnetic field. Okay, and on this south pole, force acting, it is in this direction. That is Fs. That is Fs. Clear about this? Okay, so yes, here as north pole is in strong magnetic field, Fn is greater than Fs. Is greater than Fs. Here north pole is in strong magnetic field, so Fn is greater than Fs. North pole in strong magnetic field, the force acting on north pole is more. South pole, it is in weak magnetic field, so force acting on it is less. So Fn is greater than Fs. So therefore Fn minus Fs, total force is equal to Fn minus Fs. So total force F is equal to Fn minus Fs. So here, this force is acting on diamagnetic material from region of strong magnetic field towards region of weak magnetic field. Towards region of weak magnetic field. Clear about this? Again, I will repeat this point again. The bar of diamagnetic material is placed in non-uniform magnetic field. It is non-uniform magnetic field. Magnetic field, we know that it is from north to south. Diamagnetic material is placed, obviously, in diamagnetic material, it is magnetized in opposite direction. It is magnetized in opposite direction. So this pole will become north and this pole will become south. Clear about this? Okay. Now, as this north pole is in strong magnetic field, force acting on north pole is more. South pole is in weak magnetic field, force acting on it is less. This Fn and Fs, they both are in opposite direction, but Fn is more. So force acting on diamagnetic material is from strong magnetic field towards region of weak magnetic field. These points you have to remember. Okay. So yes, again we will repeat points. First, diamagnetic material do not possess permanent magnetic moment. In absence of external field, magnetic moment is zero. In presence of magnetic field, magnetic moment is induced in opposite direction. It is behavior in uniform field, it is behavior in non-uniform field. This point you have to remember. Magnetic field is reduced, charge M becomes negative, force is acting on diamagnetic material from region of strong magnetic field towards region of weak magnetic field. Now one last point. For superconductors, what is superconductors? We know that as temperature increases, resistance increases. Okay, as temperature decreases, resistance also decreases. After some point, after some temperature, below some temperature, resistance of conductor becomes zero. Again, below some particular temperature, resistance of conductor becomes zero, and such conductor is called superconductor. Okay, resistance zero, so there is no power loss. Resistance zero means there is no power loss. So such conductors are called superconductors, and yes, that particular temperature is called critical temperature. So if temperature of object is less than critical temperature, its resistance is nearly equal to zero, resistance zero, so no power loss. Okay, so yes, it is superconductor. So yes, for superconductors, chi n is equal to -1 and mu1 is equal to 0. Chi n is equal to -1 means if external magnetic field is B, then magnetic field produced due to diamagnetic material is also B, but in opposite direction. That's why chi n is equal to -1. So see, when superconductors are producing external magnetic field lines are completely exposed. What is meaning of this? In this region, total magnetic field becomes zero. The phenomenon of perfect diamagnetism in superconductor is called Misner effect, and it is used in radiated train system. Okay, so yes, what is diamagnetic material? Its definition, okay, its behavior in uniform magnetic field, its behavior in non-uniform magnetic field. Points to be remembered: chi n is negative, force acting on it is from strong region to weak region. Clear about this? So yes, it is all about diamagnetic material. In next lecture we will study about paramagnetic material, and then we will discuss what is difference and similarities between diamagnetic and paramagnetic materials.